I'll go ahead and start the recording. Officially welcome everyone. Happy garbage day. I already pulled the cans inside, so they're not going to blow away this afternoon, thank goodness. How is homework 3 going? That's the next item up for bids, due next Monday. Any questions on that I can help with at the moment? Not yet. That's fine. You got a whole week. I will tell you, homework 3 is not as hard. I deliberately went easy on it because the goal of homework 3 is to figure out what y is. There's no interaction terms, and it's the same model. You're just predicting different versions of y with ordinal, non-proportional, odds ordinal, and nominal. So figuring out what the model is predicting is the whole goal. The next one after that will be the ramped up difficulty a little bit again. But, just kind of like a wave, like an ocean wave. Other things you can be thinking about, your homework 5 plan is due in a couple weeks. So homework 5 is your chance to practice generalized models on data that you care about. And as part of that, I basically want an outline from you about what you're planning to do, what the data contain, what type of sampling, what type of variables, what you want to know, so that I can weigh in on those choices and give you some direction. I'm going to put up the rubric that goes with homework 5 after I see your outlines so that I can make sure that it is comprehensive enough to cover all of your special cases. Ideally, you would pick one of the models we've covered up to this point, so binary, categorical, or counts. Then we will have finished, I think, proportions as well, so rates would also qualify under there. But if you're thinking of something else that is outside the scope but still fits within the class, let me know and we'll talk. If you have to do an assignment, if you have to do analyses for some other purpose that you can double count for this, do that. Okay, I'm a big fan of double dipping. Create efficiencies where you can. So if these are analyses that you had to do for your assistantship or for a thesis or for a paper and you want some feedback about the process, this is your chance to be able to do that. So you can speak with me or the TAs about your choices and we'll help you get there. And should we talk about formative assessment? Let me get the screen share going. This one, make sure the recording is still going. Looks like we're all good there. All right. So audio, video, screen share all good? Excellent. As always, if my microphone cuts out or we encounter any other technical problems, please let me know. I've got the chat open and I'm watching it to make sure that I don't miss anything. And of course, you can talk as normal as well. So we are talking about first link functions. So what is the role of a log link? What is a log link function for? Started talking about this last Thursday before break. What do we think? Everyone answer the questions. I went through and processed them this morning. What's the point of a log link?
To make the expected outcome bounded at 0.
Yes, bounded on one side. So when would you pick log versus logit? What kinds of outcomes are they designed for?
I mentioned count data in my example. So with a log link function, you can bound it at 0, but it doesn't matter how many counts you go up to because there is no upper boundary. Whereas with the logits, you have bounds on both ends.
Yes, exactly what I would have said. So log link is for outcomes that are bounded at 0 on the lower end but don't have a boundary on the upper end. So counts is one example. Continuous outcomes also come in that flavor. Things like minutes of vigorous physical activity, dollars earned in a year, heart rate, things like that. That sort of they're lower bounded at 0 but they can go up into positive infinity. A log link makes it so that the predicted outcomes from those types of variables stay above 0. And logits are for outcomes that need boundaries at both ends, so between 0 and 1. Binary is one case that we saw. Logits are also used for ordinal and nominal, so cumulative or unordered versions of logit links for the submodels, as well as what we'll see in the unit after this one, proportions. So if you're modeling something like percent correct, the lowest you can do is 0% and the highest is like 100%. Logits are going to be used for that for the same reasons. And these are examples of link functions. So I want you to know that as a keyword, because when you're looking at options in software, that's the word you want to search for. Link equals is usually what the options are referred to as, so a link function. And just as a reminder, these are transformations of the predicted mean. They are not transformations of the data. So we're not log transforming our counts. We are asking the model to log transform the predicted count that the model is trying to recreate with our predictors. So, very good. What kinds of outcomes then would Poisson and negative binomial be appropriate for? So these are some new vocabulary words, choices for conditional distributions. You can use the chat or you can talk. I'm not sure you can do icons with this, but you're welcome to try. Maybe there's an emoji for it. Poisson or negative binomial, what kind of outcomes are they for? What unit are we in right now? Let's put it that way. Make it more obvious. Counts, yeah. What's the difference between the two? Yeah, we talked about that like a week and a half ago and it's gone. We're going to do that today. I will tell you counts, like the base model is Poisson, and the negative binomial adds something to Poisson that allows the variance to exceed the mean. So it allows what I call a stretchy factor, or over dispersion is the vocabulary word, where variance is greater than expected. And we will see that which of these is appropriate is an empirical question, because if the stretchy factor reduces to 0, then that becomes Poisson. So you can basically test if that extra added parameter is helping the model fit better, helping the distribution fit better. What are the two concerns regarding zeros that we need to watch out for in count outcomes? There's two different problems involving zeros. Most of you wrote them down.
There could be no zeros at all, or there could be like multiple zeros possible, which could be like qualitatively different.
Yes, yes, so there could be no zeros. So the examples I gave in class was if you have a count distribution that's coming from a data set in which you have to have the count happen to you at least once to be part of the data. So number of times you've been arrested if you're looking at prison data, number of stays in the hospital if you have a hospital data set, and so forth. It's not enough to just subtract one and move everything over. I tried that, it doesn't work. I should have guessed it wouldn't work that way, but yeah, like I can make a zero out of this, just watch. No, you can't. Doesn't work. And then too many zeros. So the term for that is zero inflation as a keyword, and that occurs when there are more zeros than predicted by the distribution. So Poisson and negative binomial as count distributions, or distributions for count outcomes, I should say, they have zeros built in. And then the question is, how do you address the situation in which there's more zeros than expected? And that can happen if you're mixing qualitatively different populations, like she said. If you have, a population that doesn't do the behavior in question, like you have extra zeros because they would never move off of 0, mixed with a population that does do the behavior in question. So there are different strategies for addressing that, and those are distinctions that we'll start getting into this week, if not today, Thursday for sure. All right, third one. So the variety of answers on this one. This is both review and foreshadowing. So generalized linear models, how do they address the typical assumptions that we would rely on in a general model, which is independent residuals? And in that, I was thinking specifically about the residuals for different people being independent. That means that there's no expected clustering or nesting or reasons why some people would have more correlated residuals than others. That was the one that I wanted to focus on. But also normality of residuals and constant variance. So which of those are we changing and which of those aren't we changing by switching to generalized models? Start with normality. Do we have to assume that anymore? Nope. Like if I have a logistic regression, what am I assuming about my residuals if they're not normal? I can wait and be quiet too. That means I don't have to talk as much. I'll just wait y'all out. For logistic regression, the question is, what are we assuming about the distribution of the residuals? Are they supposed to be normal? No. What are they supposed to be? Starts with a B. Somebody's name, I think. The distributions that get capitalized, I think, are people's names. I think that's why. Bernoulli for the win, yeah. And the good news is that for binary, you can't be wrong. Like, that's what it is. That's what it has to be. What about for ordinal? If we fit an ordinal regression model, known as proportional odds models.
Multinomial distribution?
Yeah, multinomial. We're not assuming normal in those cases. And normal and constant variance are tied together because in the normal distribution, unlike most of the others that we'll talk about, there is a separately estimated parameter for the variance, and it's one number. That's where constant variance comes in, is because there's only one parameter. So no matter where you are on your predicted outcome, the residuals are supposed to be distributed around that to the same extent, everywhere along the regression line. In these models, though, do we assume constant variance, like in a logistic regression? No. What happens in the Bernoulli distribution? What is the variance? Yeah, I'll take finger questions on that. Yeah, tied to the mean, is that what this means? Yeah. In the Bernoulli distribution, there is no variance. It is the mean times 1 minus the mean. So there's a different variance at every point, different mean, where there's a different mean. So the variance is non-constant. Same idea within multinomial. In Poisson, what is the variance supposed to be? Do you remember? And if not, that's okay. We'll go back over it. Is variance constant in Poisson? In that one, the answer is no. The variance and the mean are the same parameter, which means the variance grows as the mean grows. So non-constant. Negative binomial is the other choice that we've seen so far for count data. That one is also non-constant. It grows as a function of the mean, but in a quadratic over dispersed fashion. So non-constant. So point being, everything that we've talked about so far, this normality and constant variance assumption is fixed, essentially. It's being replaced by different assumptions that go with the conditional distribution we're picking. So we're not assuming those things anymore. We're expecting something that's non-constant. But what about independence? Is a logistic regression model designed for independent samples? I'd say so. What about an ordinal regression model? Or nominal? Or count? Yeah, all of them are. So that assumption is still there. So that is the one way in which you can be wrong. For instance, if you have binary outcomes, they're going to be Bernoulli, but not if there's additional sources of dependency, which is the opposite of independence, meaning some reason why certain people's residuals are more correlated than others. And I'm going to call in the TAs. Okay, you listening, TAs? Giving you the heads up here. Can you give me an example of when that would happen, when you wouldn't have just a straight independent sample because some people's residuals are more correlated than others?
Longitudinal designs or
Yeah.
clustered data.
Longitudinal or clustered. So if you have different observations as occasions, the occasions collected from the same person are going to be more related than occasions from different people. If you have people that occur in natural groups, such as classrooms or schools or universities, the people from the same unit will be more correlated. Nikki, can you think of others?
I was thinking of another example of clustered in terms of like paired data. If you're asking like, children and parents, similar questions or whatever.
Yes. So dyadic or family data. So if you're studying, relationship satisfaction between partners, if you're studying, parent-child interaction patterns, that kind of thing, then people from the same family unit will be more related than people from different family units, and the model has to understand that. The solution to that we will see at least a little bit of in the second half of this class. So that's unit 5, as we're going to get into what's known as multivariate models, when we're predicting multiple outcomes from the same unit simultaneously. So multiple observations per person or multiple observations as people from different groups, that kind of thing. So point being, general models and generalized models are designed for single levels of sampling and independent residuals. If you want to change that, we have to add stuff to the model that allows the residuals to be correlated. That's still coming. All right. I think that's all we had. Yeah, that's the end of the questions. Any of that you want to hear more about or discuss, Vladimir? No?
Yes, I have a quick question, Lisa,
Sure.
and this is confusing to me sometimes because you were talking about model residuals and that these residuals follow a Bernoulli distribution. But I thought that the model residuals will follow the distribution, will follow a distribution based on the link function we are using, can be logit or can be probit, and can have a specific variance number. So what's the model residuals at the end? It is the residuals in the are the residuals in the model scale or are they in the data scale?
Okay, I think I understand the source of the difference. So it's not the residuals that are Bernoulli, it's Y. So it's the zeros and ones that follow the Bernoulli, and then the model is trying to predict up to a point with the residual being left over, but it's Y that does. It's only in the case of the normal distribution that you can talk about Y being normal or E being normal, like in terms of that. But the model is focused on E, but it's still, you can talk about E or conditional Y as interchangeable, and that starts to fall apart when you have link functions. What you were talking about in terms of the different scales is not the variance of original Y or the residuals of Y, but the variance of Y star. So this is a sloppiness in my notation that I've noticed and I need to clean up. I did it for the other class, but hadn't done it for this one yet, but it's for next year. By the way, I keep a text file that's literally called Things to Fix for Next Year for every one of my classes, and this one's already going in there. So if you've had things to add to the list, please let me know. But it's Y star is what has the variance of 3.29 if you're in logits or 1.0 if you're in probits. And Y star is the imaginary continuous variable that underlies the binary or categorical version. We don't have it. It's just a way to set a scale that makes sense.
Awesome. Thank you, Lisa.
Yes. Because it's imaginary, there is no way for us to test any kind of distributional assumptions. We do not have that information. So to me, it's like, who cares? But in terms of like what numbers you would use for residual variance, like to compute things in the model scale, that's where those numbers come from. Is the Y star assumed distribution.
Great. Thank you, Lisa.
Thanks for the question. Okay. Any other questions? All right, then how about we look at an example? Oh, underwhelming response. How about we look at an example? Yay! Yes, for those of you on the internet, my students just burst into a spontaneous round of applause. They were so excited. Example 3. I told you a little bit about this before break, but here is the full story. So these are real data. That's why they're not in the download packet. From one of my former students at the University of Nebraska. This was her master's thesis. And the story behind these data is that this was a randomized experiment where folks were brought into the lab. They were asked a series of demographic information questions, such as whether or not they had a history of interpartner violence, or IPV, and that was dichotomized into people that did versus didn't. And they were assigned to one of 3 different emotion regulation conditions. One was none, I believe. Yep. One was cognitive reappraisal, and one was suppression. And they were brought into the lab, assigned to these conditions, and after various measurements, they were deliberately pissed off. And then they were told how to address their pissed off feelings. Like, do whatever you want, try to reframe it so it's less threatening, blah, 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 cognitive reappraisal. I'm not the clinical psychologist here, so I'm just going to make some shit up. Any clinical people here? I don't see any. Okay, you can correct me if you want, but I'm just going to take some liberties otherwise. Or suppression, which is like, stuff it down, don't let it bother you. Turns out suppression is not the best strategy for you. So the question was, how do these strategies differ with respect to the outcome, which was number of aggressive verbalizations during a subsequent measurement after the manipulation, and whether the manipulation had differential effects as a function of whether the participants had a history of IPV or not. So I got brought into this as when I was at Nebraska, I was in the Department of Psychology, and one of my primary jobs was to be the department consultant. So I had a course release every year in exchange for holding office hours and helping people with their stats, which is fine. And the student came in, and her question was, as I told her, how do I transform my outcome so that it's more normal? And the outcome that she needed to transform is this one right here. So let me zoom in a little bit. This is not a couple pages in. Okay, so this is a very classic example of a count outcome. It has a whole bunch of people at 0, and then some kind of trailing off distribution after that. This also, to my eye, looks 0 inflated because there's a whole lot of zeros relative to what you would expect given that the rest of the distribution goes out here. And yeah, there's some weirdos. Like there's one person out here who said 24 mean things. And here's somebody who said, 19 mean things, and 2 people who said 17 mean things, and so forth. So typical strategies for addressing non-normality to try and shoehorn this into a general linear model would be some kind of transformation. So if she did a log transformation, that would reel in this positive tail to reduce the skewness. But there's nothing that she can do to take this pile of people who answered 0 and turn them into anything other than a pile. Like that lower boundary is a consequence of how this variable is measured, and there's nothing to be done with that. As I had mentioned, I suspect the reason why I was brought into this is because the interaction that was the whole point of her master's thesis project had a p-value of 0.06. And it was like, oh, can we just, is there anything we can do to make that thing be legit? And it turns out that once you fit the right model, she does have a significant interaction. But it's not a question of whether you want the interaction to be significant. What we want is for it to be accurate. So does this picture, let me ask you this, does it automatically imply that I need to run some kind of 0 inflated model? Can I stare at a marginal distribution like this and immediately know what kind of model I need? You're like, isn't that too simple? Yeah, you can, I think staring at these kind of pictures can point you towards a model family. All right, so the fact that I know that it's a count, I know that counts are bounded at 0, and there are zeros in this case. I know that this is probably going to be some kind of count family. I don't know necessarily which particular combinations, because the model assumptions are about the conditional outcome. So it's after all the predictors are in place, does the whole thing become Poisson or negative binomial? So you can't really get a sense of that until you put the predictors in place. In this case, because I'm using a pretty straightforward model in which the only predictors are IPV and what group they were assigned to, I can get a proxy of that by looking at each of the different cells here. And what it looks like is that there's a sort of a different distribution in each cell. The The zeros are much more common in this particular configuration, this column in particular, than in any of the others. So I would argue that there is no universe in which this outcome is going to have a normal distribution for its residuals with constant variance. Like, that's just not going to happen. So we need to do something else. Backing up. Okay. So data pre-processing steps. I'm importing the data as stored in Excel. I am doing my own dummy coding here. I'm not treating this as a factor variable because then it corresponds much more directly to a linear model's representation. And because this is a model in which the interaction was the whole point, I want it to conform to the linear model representation as best I can. So I have n versus c and n versus s as new variables to be created. N versus c is none versus cognitive reappraisal, and n versus s is none versus suppression. So I'm setting it up so that none is the reference group, and then each of my dummy codes here gives me the difference relative to the others. So that means that if I have 3 groups, how many possible pairwise differences might I be interested in across my 3 groups? How many different combinations of 2 might I want to compare? Not a trick question, don't think too hard. If I have 3 groups, how many comparisons might I care about? This is a finger question. Are there emojis for like letters and numbers? Have they gotten to that yet? Everyone's going to check now. Oh, we found one. Yeah, 3. Excellent. So now I can expand the range of what I call a finger question, right? Because you can use your fingers to toggle to your screen. Yeah, 3. I might want to know if cognitive reappraisal is different than control, if suppression is different than control, and then if the 2 non-controls differ from each other. Right? I might want to know all those things. Typically, people don't include conditions unless they care about them, right? Like they're going to the trouble to include a condition and assign people to that condition. So given this coding scheme, in which none is the reference, which of those 2 comparisons am I going to get directly out of the model, and which am I going to have to ask for after the fact? How about we take votes? We'll turn this into multiple choice. Okay, so none versus cognitive reappraisal. Is my model going to tell me those comparisons directly? It's a little bit better. This is the stated code. Here's the corresponding R code that does the same thing. Is my model going to tell me about none versus cognitive reappraisal? Condition 1 versus 2. Not a trick, I swear. Yes, it is, because that's what this variable was designed to tell me, n versus c. Likewise, am I going to get none versus suppression? N versus s. Going to give me that one. How about the cognitive versus suppression? It's not going to give it to me directly. But can I ask for it indirectly?
Are you gonna use Lincoln for that?
Yes, I am. It's back, baby. Linear combinations, simple slopes, and interaction terms. They happen in any kind of model, generalized or otherwise. And homework 4 is going to ask you to remember that. That's why I'm hitting this. This is foreshadowing. Not homework 3, not the one that's due Monday, but the one after that on counts. Yes. So that's the only data manipulation that I need to do. IPV is my covariate, is already coded into 0 and 1, so I can work with it that way. All right, so then I did some plotting, and I came up with this as the too long didn't read version. Okay, this table. These are descriptive statistics as well as predicted means from 3 different kinds of models that we're going to look at. So the sample sizes across cells are unbalanced because even though we can randomly assign people to a motion regulation condition, we cannot randomly assign them to whether or not they have a history of IPV. That's already done. So that's why there's differences across these combinations. There are, fortunately, fewer people that have IPV than not, in most cases, the suppression condition notwithstanding. What do you notice about the standard deviations across these 6 cells here? Do they look similar? I would say no. My visual analysis suggests that a standard deviation of 0.04 means this variable is functionally a constant. And indeed, the max value is 1, whereas the maximum value is like 24 on this one, with correspondingly larger standard deviations, and the largest in the bottom cell here. So yeah, each of these possible means has differential variability around that, and the model needs to understand that. So if I just ask for the predicted mean for each of these cells and the standard error of that mean from the raw data, this is what I get. So the standard errors are a function of not only the standard deviation per cell, but also the sample size, which is why they're still not going to be the same. And then I have the predicted mean from the model that includes all 5 degrees of freedom needed to separate these 6 cells. So if I have a 3x2 design like this, I have a main effect of condition, which soaks up 2 degrees of freedom, differences across the 3 groups. I have a main effect of IPV, which soaks up 1 more, and then the interaction term of the 2 soaks up 2 more. So that's 5 degrees of freedom plus the intercept for 6 gets me back to the 6 cell means. So this is an example in which there's no misprediction per se. I have made the model as complex as it needs to be to fully differentiate these 6 different groupings. Now, if you look at the column for the mean under raw data here, under normal distribution, under Poisson, and under negative binomial, do you see anything that strikes you as unusual or unexpected? Anything of note across the 4 mean columns?
Do
Do you
they
see?
always have the same exact values all
Yeah, they
over the
do.
place?
Yeah, they do. So the goal of the model is to recreate these cell means. The normal distribution is going to do it without a log link. The Poisson actually, this one has the log link to it so that they're on the same scale. And this one are using a log link function as well. So no matter how we set this up, because we are looking at mean differences and we put in all 5 possible degrees of freedom, we're going to get the right means. The question is, what does the model think the variability around those means should be? And thus, what is the variability around the mean differences? That's where the differences come in. And if you look at the standard errors across these different configurations, you can see they're quite different. So then the question is, which one is the most likely representation of the data? So I have all of these models in here, but I wanted to make that point that the means we get back are going to be right. It's the errors around them that we're deciding on. All right, roll in. So equation time. Here's my linear predictor. So note I have AGR for aggressive verbalizations with a hat on it to convey the idea that this is the model predicted mean for a number of aggressive verbalizations. And I'm doing that with an intercept, a simple main effect of IPV, the 2 simple main effects for condition, and then the 2 interaction terms. So there's my 5 possible degrees of freedom. So if I want to know what the difference is between the no and yes IVP conditions, that is given to me by this linear combination. I will get one of them for the none group, and then I can ask for what it would be in these other groups. Likewise, if I want to know what the difference is between conditions, each pair of conditions, all 3 of these, as a function of IPV, then the model tells me that this way. So the rules for this are still the same as what we talked about at the beginning of the semester. For whatever slope you're interested in, such as the IPV slope, you go into the model, you find the terms that have IPV in them, you bring them down, and you factor out the variable the slope is for, and the linear combination is what's left. So we will use lincom in Stata or GLHT in R or estimate in SAS to get all of these missing combinations. So let's first look at, from a generalized perspective, the ANOVA that the student went with to begin with. If I say ANOVA, if we look at the pieces that can make something an ANOVA, what am I talking about? What kind of outcome is ANOVA for? Analysis of variance. Binary outcome? Are you thinking of predictors? Yeah, ANOVA for what kind of outcome? ANOVA is a special case of a general linear model. That helps.
Yes.
Yeah, continuous, conditionally normal. That's what ANOVA is for. So ANOVA, that language, refers to a normally distributed outcome in terms of the residuals, conditional outcome, and categorical predictors. So that's what we're starting with. Just we're putting it in that way of thinking about it within generalized model software so that you can start to see the connections. So in SE first, we have GLM, which is a more general package for generalized linear models that we're using to be able to assess distribution fit, because the standard like logit and ologit, those ones don't have indices of that. So we're going to dabble across different packages to get all the information we need. Agar is my outcome. And then here is my, my linear model. Hashtags here, or pound signs for the interaction terms. I'm writing everything out here for completeness. I'm asking for it to be estimated using maximum likelihood, so it's comparable to the estimator for the other ones. And then this part right here, this is how you tell a statistician what kind of model you want. Link equals identity means no link. Family Gaussian means normal distribution. So these are the things that we can switch out with other kinds of links and other kinds of distributions as we need to. So the output looks a little bit different than what you're used to from this. It tries to help you by telling you what kind of variance function you're using and what kind of link you're using, and the answer is none, essentially in this case, and normal. It gives you this thing right here, which is going to be our index of distribution fit, but not yet. This is just a restatement of the residual variance of the model as one parameter. We go down here and we have our coefficients. Do I have, let me see what I have. We'll look at those in R, since we're trying to keep it balanced across software packages. So here are the 6 parameters in my model, intercept plus the 5 slopes. Minus 2 log likelihood, that tells me the shortness of the model. Here is an example, in case you have forgotten, of how to generate an overall hypothesis test for the model. So the test statement in Stata, you add each slope that you want to test simultaneously, set equal to 0. And this is going to recreate the overall model test, which is not given in this software. It is in other versions of it, but not in this particular routine. Here is the one that my student was most interested in. This is what ANOVA language would call the omnibus test of the interaction. So this is the joint hypothesis test of the 2 interaction slopes that together imply 3 different sets of slope differences. So it's 2 slopes lumped together, chi-square of 5.7, and then a p-value of 0.06. So that was the borderline one that motivated the story. I used margins to get predicted means in logs. So this is in the original, or excuse me, we're not in logs yet. This is the original scale. And then the simple slopes. So this is the one for IPV that's given by the model. The effective IPV for the none condition starts with the IPV slope, and then it adds how that slope would be changed by being in the other conditions. And these are not yet activated because this is the none group as a control. Whereas for the second one, it's the IPV slope plus the interaction for how it differs in the cognitive reappraisal condition. And then the last one is the IPV slope plus how it differs in the suppression condition. So we get all three possible simple effects for IPV with this code. There are more than that in terms of simple slopes for condition. So we have pairwise differences between conditions within each of the IPV other variable rows or columns. So the same principle holds here. If I want to know about the difference between none versus cognitive reappraisal, this line is what's already given by the model for IPV no. Likewise, actually no, not likewise, we'll say this is how I would get it for likewise, this is what it would be for none versus suppression for IPV equals yes. And then we get into linear combinations. So -1 and 1, that's how we get the cognitive reappraisal versus suppression. So what would it be in suppression minus what it would be in cognitive reappraisal gives us that model implied difference. So this is the one we would have to ask for. Likewise, if we want to know what it would be in the IPV yes condition, then all of these are linear combinations. So we start with what is the effect in question, and then what modifies it in terms of which of the other groups. And then last but not least, are simple interaction contrasts. This is not something I think you've probably seen a lot of, but that two-slope interaction term implies three different sets of simple slope differences. So the first one is whether the difference between none and cognitive reappraisal differs by IPV status, or alternatively, whether the effective IPV status differs between those two conditions. The second one is the same idea of none versus suppression, and then the third one is the model implied, does the effective IPV differ between cognitive reappraisal and suppression, or vice versa? Does the effective manipulated group differ as a function of whether you have IPV history? So Status spits out a whole bunch of output for that. I decided to use the more condensed version to go through the actual results using R. So Stata folks, any questions on any of this coding? Let me know if that changes. You're going to see it a couple more times throughout the example. R folks, I am back to using base R, the GLM package for this, because we're just using, this is just a standard linear model, ANOVA land, but I'm doing it using maximum likelihood so that the results are comparable across all of the different variants that we're going to see. So this is how you tell it in stats language in R what you want. Family equals Gaussian link equals identity. That means a general linear model. So the model itself, then I've got my formula here. 1 to remind myself that the intercept comes first, then the three main effects, and then the two interaction terms, in which the colon is the abbreviation for interaction in this language. Okay. How about we practice going through the coefficients, since we haven't done these in a little while. How's that sound? Why not? Intercept. Given my coding scheme, who is that for? Go down the list here. Someone who doesn't have a history of IPV, interpartner violence, and somebody who is in the N group for none. So that's my reference cell in this type of design. You can think of it as a reference person too. Now that person has a predicted count of 2.7 mean things. So this is in the original scale of counts because we're predicting the expected value, the mean count, without a link function. This is a standard ANOVA model, just estimated with maximum likelihood for comparability. Going down the list then, this is the effective IPV after controlling for experimental condition. Is that the end of my sentence, or do I need to keep talking? My sentence was, this is the effect of IPV after controlling for experimental condition. Thumbs up for good, thumbs down for keep talking. Keep talking. See, internet, my students are so excited about this, they want to hear me keep talking. Now, I have to get it right, that's why I have to keep talking. The irony, of course, is that I don't want to keep talking today, but I'm contractually obligated. So, IPV, this is specifically for which group? Given the interaction terms. Your choices are N for none, C for cognitive reappraisal, or S for suppression.
The none.
Mm-hmm. The none, because that's how I always label my variables. I would highly encourage you to come up with your own system of labeling things that makes sense to you and that you can use consistently throughout your work, because it will save you time. The way that I label things is like whatever the zero group is versus the one group. So none is the zero group in both of these new variables, and so that means this is the difference between people who have a history of IPV relative to people who do not. So within the none group specifically, people who have a history of IPV say about a third more mean things in this experiment, which is not significant according to the p-value. How about these two together? These are the group differences of each of the other alternative groups relative to none as the reference. After controlling for IPV, good enough, or keep talking? These are the group differences of each alternative group relative to none after controlling for IPV. Good enough, or keep talking? Got plus signs, or thumbs up signs. In this case, it's the same issue. These are both conditional and IPV equals 0. So these are the effects of her manipulation in the subpopulation that does not have a history of interpersonal violence. So it looks like people who were told to cognitively reappraise the situation said almost 2 fewer mean things. Within that subpopulation, people who were told to suppress rather than not told anything say 1/3 fewer mean things roughly, but that's not significant. So it looks like so far the story here is a whole lot of nothing. Wait for it though. How about the interaction terms? Let's go this way for this one. So negative 1.79 is the group difference of how cognitive reappraisal is nicer than the none group, specifically in people without a history of violence. In people with a history of violence, what happens to that slope? And your choices are more positive, less positive, more negative, or less negative. Which pattern is this? We got 1 vote for more negative. Head nod. They're both negative signs, so that's usually the indicator. So does that mean that the effect of the manipulation is stronger in people with a history of violence or weaker?
Stronger.
Stronger. More anything means stronger. However, not significantly, according to this model. How about, let's go this one, because this is a tricky one. This N versus S is the group difference of the manipulation for suppression versus control in people who do not have a history of violence. In people who do, what happens to it? I would accept two different answers on this one.
It seems like less negative, but it is becoming like over zero, like positive value. So I'm not really sure how to interpret this.
Yeah, me neither. This is a situation in which the language fails because it is
Less
moving it off
negative?
of negative. Go ahead.
Less negative or more positive?
Yep, less negative or more positive. Yes, and by the way, I have to go to great trouble in your homework to make sure that that is not an ambiguous answer most of the time. And whenever it is, you will see two choices instead of four. Like, is it moving to the right on the number line or the left on the number line? So yes, this one is taking the coefficient from negative, adding the 1.77 to it, and the result is positive. So this is, I would say, less negative or more positive would be correct. However, this one is also non-significant. So if we look at just this much, the two interaction terms here, the p-values for them are 0.40 and 0.14. Yet somehow, the interaction omnibus p-value was 0.06. So how can that be? How is it that the omnibus interaction lumping these two together had a p-value of 0.06, yet each of them on their own looks to be decidedly non-significant? What are we missing? Do we have all the information yet? Which comparisons don't we know about yet?
C versus S.
Yeah, the non-reference groups. So if I just eyeball these things, do you think -1 and 1 are different? Could be. Yeah, we don't know. So this is, the point that I'm trying to make is that whenever you have these group-based designs, you only get part of the story. And you might be tempted to conclude, based on the part of the story you have, what the whole story is. But in that case, we would be led astray. Because it looks like where the story is, in this particular example, is between the C versus S. Like those are going to be different. But we don't have that here. So we're going to go through the process of asking for all of them so that we can get that. So yeah, the p-value for the interaction term is almost significant, even though neither of those contrasts is, because we're missing the third one. So I'm going to get predicted outcomes from this model. I did that via prediction function in R, or margins in Stata. And in this case, there's no link function, so I'm just going to ask for type equals response. And then I have the all possible combinations of IPV and group membership here. And here is my predicted outcome table. These are the means and the standard errors that I put into the box earlier. And I have one of them highlighted here. Here's a predicted count of 0.15. And here's the confidence interval around it. And R did not type this, but I did. I said, uh-oh. Any guesses as to why I may have said uh-oh on this particular confidence interval? Predicted mean ranges from a low of -1.3 to a high of 1.6.
It doesn't make sense because negative.
Yeah, it doesn't make sense because this count is bounded at 0, and the confidence interval is like, no problem, you said -1.3 mean things. Does that mean they said nice things? I don't know, maybe that could make sense, but that's not how it was measured. So yeah, this confidence interval is a consequence of this idea that every single cell in this design should have the same variance to it. Now that's not the case, visibly not the case. We could estimate a general linear model that has different variances per cell. That is possible to do. Finding software to do it is a little bit tricky, but I know how to do that, and I can send you examples if anyone's interested. But rather than going that route, I think that we can change the model to say, hey, this is a count outcome. Can you fit a count distribution to it that doesn't have all 6 variances be different? Instead, it has the variance be different as a function of the predicted mean. So it's a little bit more parsimonious way to solve this heterogeneity problem. But here's the results that we have from this model. Let's see how much of this I can fit on the screen at the same time. So here's a picture. Whenever you are dealing with interactions of this kind, your readers need a picture. Absolutely. Like there's no other way to keep everything straight. So what I have in the picture then is predicted number of aggressive verbalizations as a function of yes or no IPV, so in different colors, and then the 3 different conditions are across the x-axis here. And the predicted means are in the table for reference. So if we go through all of this list of simple effects here, we can take and find them everywhere on the graph. So for instance, the first one here, what is the effect of IPV in the none condition? So to get that, we need at a minimum the slope that goes with IPV, and then both of the interaction terms are shut off because we want the reference group. So they would be set to 0 and cancel out. That's going to give us the vertical distance between the red and blue lines in the left-hand side here. Likewise, if I want the IPV effect for the cognitive group, then I need to start with the IPV slope, turn on the interaction term that makes it for the cognitive group, and that gets me to this vertical distance in the middle. And then the third one is going to give me this distance out here. And if I look at the p-values that go with these things, it looks like the first 2 are not different than 0, but the third one is. So the IPV group is higher than the no IPV group out here. So that's one set of simple effects. If I want to go the other way, pairwise differences comparing within the lines. So first, if I go with the blue line for no IPV, then I need the group difference. I don't need either interaction term, and that gives me no versus cognitive. The second one is no versus suppression, so I just need the group difference and none of the interaction terms that turn on IPV, and that is going to be this point on the left versus the corresponding blue point on the right. So it looks like the first one is significant and the second isn't, and then the last one is the linear combination. So if I want to know the difference between the non-reference groups, then I give the first one a -1 and the second one a 1. So this is going to tell me how suppression differs from cognitive reappraisal as the contrast, and that's where we see the -1, 1, and that gives me this blue dot versus that blue dot, and that one is significant as well. So it looks like none versus suppression is not different, but the other 2 are. We can do the same thing within the red lines, and we see the same type of pattern where none versus cognitive and cognitive versus suppression is different, but none versus suppression is not. And then last but not least are the differences in the differences. So this interaction term, omnibus, can be thought of as 3 different contrasts. If I go IPV first, I can ask whether the left vertical distance is different than the middle one, whether the left one is different than the right one, or whether middle and right are different in terms of the vertical distances. So there's 3 different what are called interaction contrasts, differences in simple slopes. So does the effect of IPV differ in this condition versus that one, the first one versus the third one, or the second one versus the third one? That's one way to approach it. The other way is to think about the slopes. So for instance, the slope from none to cognitive, is the blue slope different than this red slope? Is this blue slope different than that red slope? And then is the implied slope that links the first and the third different than the implied slope that links the first and the third for red? So there's 3 interaction contrasts. Our results so far have only told us about 2 of the 3. We're missing the ones that are cognitive versus suppression. So that really is the big one. The last one down here is an implied difference in the slopes. And survey says, yep, that's the one that pops. So the reason there is a almost significant interaction is because of these two sets of differences, where there's no difference between as a function of IPP in this condition, but there's a big difference in the opposite direction here, according to this model. Okay, how are we doing? It can get confusing, but if you sort of go through the process of outlining, like, what are the possibilities and which ones do I have and which ones do I not have, then you can get everything that you want to know. So these are the possible interaction contrasts in terms of simple slopes. The model gives us 2 out of 3. It gives us the 2 that are tied to the reference group, and that's how you know what you're going to get. If I made a plot here, this is actually a SAS plot, but this is looking at the distribution of residuals. We can see that this is not a good fit. So this top left here displays the scattering of residuals as a function of the predicted outcome. If the normal distribution were a good match for this outcome, then we would see these dots be scattered around the line to the same extent. The whole thing would be flat and even. But instead, what we see is they grow as the mean grows. So there's more variability towards the middle and the ends than there is at the beginning. That's a classic count outcome where you see this like fan shape with your residuals around the prediction. If the residuals followed a normal distribution, they'd be on this line, and clearly they don't. So this suggests that this is not the right model. Not just the non-significance, that's irrespective, but the fact that it's predicting counts that go below 0 in terms of the confidence interval, and it's assuming constant variance where clearly there's non-constant for that. So then we can try some other ones. So that was normal. Next is the tour of the Poisson models, and there's going to be 4 different versions of these that I attempt. All of them are going to have a log link. So that log link is needed to solve the out of bounds problem. If we throw a log link on it, that means the predicted counts cannot go below 0. So that solves that. The question then is, what kind of distribution do we need? And to what extent does the variance exceed the mean? That's step number 1. And then to what extent do we still have these extra zeros after we build in the linear predictor of our group differences that's going to partially explain why some of the cells have more zeros than others? So that's what is on tap for Thursday, but not today. Deal? Internet scores of applause once again. They're blown away. With the few minutes that I have left, I want to give you a heads up for an email that I'm going to send regarding participation in research. So you will get an email from me about completing a mid-semester course evaluation for research purposes only. I don't think I mentioned it to this class before break, but I'll do so now. There are folks who are interested in studying patterns of course evaluations and how they relate to personal characteristics of the students and personal characteristics of the faculty. And so I agreed to participate in this class, meaning I could let them ask you to participate. So you'll get a special Qualtrics link and code via email to complete an evaluation based on your experience in this class. The difference is that it's not being used at the end of the semester, so it's not actually tied to anything official from the university, but it does have extra demographic questions so that they can actually look at the influence of bias and personal characteristics. So I would highly encourage you to take the 5 minutes it will take to fill out this form. I don't think they're collecting much qualitative data, so it shouldn't take very long. And I don't know who completes it and who doesn't, but I'm supposed to get some sort of summary as a token of their appreciation. So be on the lookout for that, and I would encourage you to do that if you were able to. Since, we all do research, right? It's only fair that we participate at least a little bit when push comes to shove. All right. Anything else?
I should mention.
Yeah, go ahead.
I feel like I should mention in all transparency that I am part of that research team. So thank you. And in case you consider to participate, Lisa, thank you for volunteering. And I just want to reiterate that it isn't going to affect your grade or participation or anything in this class. And
it won't affect me either.
I'm not grading anything in your class either. So my responses you would provide there are not influencing your grade in this class either.
Yep, it's just for research purposes. Okay. Any other comments or questions about counts or research or enthusiasm? Okay, then thanks for bearing with me today. I hope to be back in front of you on Thursday. I'll let you know if not. All right, take care. See you on the other side.